Hello friends, welcome to Best Tutor. This is Rama Vishwanathan. In today's class, we are going to learn about irrational numbers. We have already learned that what are rational numbers, what are the elements of rational numbers. In today's class, we will learn in detail what are irrational numbers and how do we prove that square root of non-perfect squares is an irrational number. Let's get into the details of it. So, we have already discussed about rational numbers and we will move on to irrational numbers. The numbers which do not belong to the set of rational numbers are irrational numbers. So, we have already learned that terminating decimals and recurring decimals belong to rational numbers. Then what are the types of decimals that belong to irrational numbers? They are non-terminating and non-recurring decimals. In the sense, the process of division never ends nor the quotient repeats. For example, 0.1, 0.1, 0.1, 0.11, 0.111, so on. In this example, if we consider, there is no end to the process nor the decimal part is being repeated. Such a decimal belongs to irrational numbers and the set of irrational numbers is represented by the letter Q bar. Okay. We have already learned that all natural numbers, for that matter all integers, belong to rational numbers. Integers is a subset of rational numbers. All fractions, and decimals. There are two types of decimals which belong to rational numbers. They are terminating and recurring decimals. These all belong to rational numbers. So, the third type of decimal, that is non-terminating and non-recurrent decimals, belong to irrational numbers. What about square roots? If at all I have square root of 2, square root of 3, square root of 4, root 5, so on. This appears to be peculiar out of all these four examples. The reason being 4 is a perfect square and the answer of root 4 is going to be 2. So, 2 belongs to rational numbers. How about root 2, root 3, root 5, so on? They belong to irrational numbers. How do we prove it? Let us prove that root 2 is an irrational number. How do we prove it? We will prove it by contradiction. Let us assume that root 2 is rational. We are taking the quite opposite of the given question. We need to prove that root 2 is an irrational number. I have assumed that root 2 is rational. So, at some step or the other, we are going to get a contradiction. If root 2 is rational, root 2 should be represented in the form of P by Q, where P and Q do not share any common factor. P comma Q belong to Z and Q is not equal to 0. This is the definition of rational number. So, I have assumed root 2 to be rational. So, root 2 should be in the form of P by Q. If I square it on both sides, I get 2 is equal to P square by Q square. This implies P square is equal to 2Q square. That it means that P square is a multiple of 2 or P square is an even number. If P square is an even number, it means that P is an even number. Right. If P is an even number, it should be written as a multiple of 2. So, I will take some number m in such a way that P is equal to 2m. I repeat it, we have to prove that root 2 is an irrational number. We have assumed root 2 to be rational. If root 2 is rational, it should be in the form of P by Q, where P comma Q belong to Z, Q is not equal to 0. I squared it on both sides, we get 2 is equal to P square by Q square. This implies P square is equal to 2Q square. It implies P square is an even number because of this 2. 2 is a factor of 2 into q square is equal to p square, therefore p square is an even number. If p square is an even number, p is an even number. So I should be able to write p is equal to 2 into some number. That number I have taken it as 2. Now if we square on both sides, we get p square is equal to 2m square or 4m square. P square is equal to 4m square. But here we have got p square is equal to 2q square. If I substitute here, this implies 2q square is equal to 4m square, or q square is equal to 4m square by 2, and hence we get 2m square. Hence we have got q square is equal to 2m square. This implies q square is an even number. If q square is an even number, q is also an even number. Here we have p is an even number. Now we have proved q is an even number. That means they share a common factor too, which is a contradiction to the definition of rational number. This is a symbol for contradiction. We have, in the beginning of the procedure, we have assumed that root 2 is a rational number. So root 2 can be written in the form of p by q, where p and q do not share any common factor. But now we have ended up with a contradiction where p is an even number and q is an even number as well, which is a contradiction. Therefore our assumption that root 2 is a rational number is wrong. Our assumption that root 2 is a rational number is absurd, which is a contradiction. Therefore, root 2 cannot be a rational number, so it should be a irrational number. Similarly, we can prove that root 3, root 5, root 7, so on are irrational numbers. So we came to a conclusion that the set of irrational numbers consists of all the square roots of non-perfect squares. Example, root 2, root 3, root 5, root 6, so on. These all are irrational numbers. So, in today's class, we have learnt how to prove root 2 is an irrational number by method of contradiction. Similarly, we can prove that root 3, root 5, so on are irrational numbers. Let us meet in the next class. Thank you.